Today we're going to talk some more about the second derivative. Remember, the second derivative measures concavity. That is the shape, be it sort of the smiley shape or the frowny shape. The smiley shape is the one which indicates that the second derivative is positive, and the frowny shape is the one that indicates that the second derivative is negative. This is what the second derivative tells you. This is called the concavity. This is concave up. This is concave down. I'm going to do an example where I give you a function and you have to tell me where is it concave up or concave down. Not looking at the picture, but looking at the formula. Alright, give me intervals where f of x is concave up and concave down. And this is the function. Alright, we're going to do this just like, this is almost exactly like the question, give me intervals where f is increasing or decreasing. But instead of, for that question, use the first derivative, because that tells you if it's increasing, decreasing. We do the same procedure, but we use the second derivative, because that's what tells you if it's concave up or down. I hope you remember the procedure. We're going to find the second derivative first of all, then see where it equals 0, then make a chart, plug in values in between. I think it'll come back to you. So, in order to find the second derivative, you must first find the first derivative, f prime of x. I go through here, take the derivative. I get 4x cubed minus 24x squared plus 36x, right? And then I do the derivative again. This is my second derivative, 12x squared minus 48x plus 36. I'm going to simplify this as much as possible and then determine when this equals 0. So to simplify, we can factor out a 12 everywhere. And then what remains is x squared minus 4x plus 3. I know my 12's. And then this guy here, you can factor that, right? 12, and then I'm going to be x minus 1, x minus 3. Okay, this is the simplified form of f double prime. In order to make that chart, like I always do, I need to find out when this equals 0 and then make the chart. So when is f double prime of x equal to 0? This is easy to say since I have it factored already. You can say this 12 doesn't matter. That can't make it equal to 0, but this does. X minus 1, this can be 0 when x equal 1 or when x equal 3, right? X equal 3 will make this part 0. Okay, so these are the two, they're not critical numbers. They're points when the second derivative equals 0. I'm going to put them on my chart and then plug some stuff in. It'll be great. All right, here's my chart. I have these two special x values, 1 and 3, and down here I am going to write the signs of f double prime. Usually we put f prime here, but I'm doing double prime because the question was about concave up, concave down. So f double prime is 0 here and here. I got to plug in points in between everywhere. So to the left of 1, let's use 0. F double prime of 0 is, plug it in, 12, 0 minus 1, 0 minus 3. This is positive, negative, negative. So this is positive. So positive over here. Same stuff that we've been doing the past few times. This little chart method works in many different types of problems. 2 I choose in the middle. Plug it in. 12 times 2 minus 1 times 2 minus 3. This being, well, positive. That's the 12. 2 minus 1 is positive. 2 minus 3 is negative. So this is negative in here. And then finally, to the right of 3, I'll use 4. 12 times 4 minus 1. 4 minus 3. These are all positive. Positive, 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 positive up here. Okay, this is my chart. Positive, negative, positive. So I think we can say the answer. Remember the question was, give me intervals where it's concave up and concave down. So I'm going to say it is concave up on the intervals where it's positive. That would be minus infinity to 1 and 3 to infinity. And it's concave down on the one in the middle, interval 1 to 3. All right, excellent. Finally, we're ready to discuss the second derivative test. Remember we had the first derivative test? This was a method for telling where the relative max and relative min are. The second derivative test is another method which uses the second derivative instead of the first. And you'll see the second derivative test is actually a little bit easier to do. The second derivative test, let me just say, It's another way to identify the relative minima and maxima. We used the first derivative test to do that before, but there's another way to do it. And the benefit to the second derivative test is right here. No chart required. It's true. You don't have to make that chart and then do the pluses minus. Remember the first derivative test? You find the critical numbers, make the chart, you do the plus minuses for the first derivative, and then if it goes up and then down, then it was a maximum. If it goes down and then up, then it was a minimum. The second derivative test is a way to do this without looking at the down and then up or the up and then downs. It's based on the second derivative. Check it out. If you have some point and you're not sure if it's a minimum or a maximum, well, if the curve does that, then it's a maximum. And I will notice, what can you say about the second derivative? Well, in this picture, it's a relative maximum, which is because the curve is going like that. So it's because, the reason it's a max is because the second derivative is negative. So a relative maximum, this is a fact, a relative maximum has f double prime of x being negative. And a relative minimum looks like this. It is concave up at that point. So a relative minimum has second derivative being positive, right? So this is how you can use the second derivative to determine if something is a minimum or a maximum. I'm going to write down in words how you do this, and then we'll do an example. All right, this is the second derivative test, how you do it. First of all, you have to find the critical numbers in the same way that you did using the first derivative test. That is, you say when the derivative equals 0, when the derivative does not exist. And then, for each critical number, you plug it into the second derivative. If the second derivative is positive, that indicates that this critical number is a minimum. If the second derivative is negative, it indicates that the critical number is a maximum. And if the second derivative is equal to 0, or I should say, if f double prime does not exist, in that case, you cannot make any conclusion using the second derivative test. This is the failure case. If this happens, then it means the second derivative test is not going to work for you. You will not go to space today. You just have to go back and use the first derivative test instead, which always works. This is I said the second derivative test is a little easier because you don't have to make the chart. That's true. This is the downside. Sometimes it just straight up doesn't work and you have to sort of retreat and use the first derivative test again. It's a shame, but that's how it works. Let's do a couple examples. Okay, how about this one? Let's find and identify the relative extrema for this function. Now, I want to use the second derivative test just because that's what we're talking about today. But if you encountered this question on a test or something, on one of our tests in class, you can do whatever you want. You can use the first derivative test or the second derivative test. They both are just two different methods of answering the same question. I might just tell you to use one or the other because I want to make you show me on the test that you know how to do both. But anyway, let's do it using the second derivative test. How we do it? First, you find the critical numbers as usual. So I have to take the derivative first. This is going to be 12x squared plus 14x minus 10. And then I want to simplify this as much as I can. I guess I can factor out 2 from everything. 6x squared plus 7x minus 5. Now we can factor this. I hope we can factor this. This one is a little tricky because I got the 6 out front, but it has to be, like one of these, right? Let's think about the signs, first of all, are going to be a plus and a minus because this is negative, that's positive. And then these two numbers, they have to multiply together to be 5. So it's either going to be plus 1 and a minus 5 or a plus 5 and a minus 1, all right? And then these numbers in the front, they have to multiply. I got my x's, of course. These x's will have coefficients. They have to multiply together to be 6. And then it all has to add up appropriately. Now, the way that I usually do these is just sort of by trial and error, guess and check, if you will. I'm going to write down all the possible combinations that I just said. Can I? These two numbers have to be 1 and 5, or maybe 5 and 1. And then these two numbers have to be 1 and 6, or maybe 6 and 1, or maybe 2 and 3, or maybe 3 and 2. There's a lot of possibilities for what these could be. How do we tell which is the correct combination of guys here? You have to just try to do the FOIL and see if you actually get 7x in the middle. So for example, this first one, if I just read it straight across, it says plus 6x minus 5, which would add up to plus 1, which is not that. Okay, what if instead of that I used the 1 here and the 6 here? Then on the inside it would be 1 times 1. On the outside, 6 times 5. That's not going to add up to 7. You got to just try all the combinations until you get something that adds up to 7. Maybe I'll look and see, can we make this add up to 7? How about 3 times 1 and 2 times 5, right? That 3 times 1 would be 3, and then 2 times 5 would be 10. If we can make the 10 positive and the 3 negative, I think it'll add up to 7. So I'm going to make it... I want it to add up to 7, so I got to make a 10 and a 3. 10 being 5 times 2, so this is going to be a 2x here, and then a x here, and a 5, like that. Here I'm going to do 5 times 2, which is 10, and I want that to be positive. And then the other one is going to be minus 1 and a 3 here, right? Minus 3x plus 10x is 7x. All right, I guessed it and I checked it. Okay, can we solve this then? Well, no, this is the simplified form of f prime of x, right? Every so often I like to do one of those tricky factoring with the extra number on the front there. Okay, can we find the critical numbers? To do that, you set this equal to 0. All right. What do we get? 2 times, well, you make each of these things 0. The 2 doesn't matter because the 2 cannot be 0. The other parts can be 0. 2x minus 1 equals 0. 3x plus 5 equals 0, right? Solve for x each time. 2x equal 1, which means x is a half, so that's one critical number. And here, 3x equals minus 5, x equals minus 5/3. That's another critical number. So here are my 2 critical numbers. Remember how to do, we're doing the second derivative test. It said first, find the critical numbers, then plug each critical number into the second derivative. Actually, I never even found the second derivative. Let's find the second derivative. It's easy. I shouldn't have erased that. I erased my first derivative. It said 12x squared plus 14x minus 10, right? To find the second derivative, you need to take the derivative again. Now, if you look here and take the derivative again, you're going to have to use the product rule, which I'm not really into that, given that I could just take the derivative here again, right? This is the first derivative, and this is an easy thing to take the derivative again. So I'm going to take, when I find my second derivative, I'm going to use this version rather than that version. They are equal, but this one's a lot easier to take the derivative of. It says 24x plus 14. Okay. I don't need this anymore. All right, remember the second derivative test. It says, find the critical numbers. We did. Plug the critical numbers into the second derivative. Okay, so I'm going to do f double prime of 1/2. No chart, remember? What do we get? F double prime of 1/2. It's going to be 24 times 1/2 plus 14. And what's that? This is 12 plus 14, which is positive. All you care about is it positive or negative? And the second derivative test says if the second derivative is positive, that means x equal 1/2 is a relative min. Remember, positive means the shape goes like this, and my point is right at the bottom there, so it's a relative minimum. Okay, what about the other one? F double prime of negative 5/3. Plug that into the second derivative. 24 times negative 5/3 plus 14. This is going to be, simplify my fractions, 24 divided by 3 is 8. So this is negative 8 times 5, right, plus 14. This is negative 40 plus 14. This is negative. And that means this thing is concave down. It looks like that, which means my point is at the top. So x equal minus 5/3 is a relative maximum. That's how we do the second derivative test. I just wanted to see an example where the second derivative test fails, remember it is possible for the second derivative test to fail, and then you have to just go back and do the first derivative test. How about this? This is actually an example that we did a couple times ago, using the first derivative test. This one was f of x equals 6x to the 2/3 minus 4x. Remember that guy? And I want to find, as before, find the relative extrema. All right, 6x to the 2/3 minus 4x. Now, we did this last time. First, you find the critical numbers, right? You do the derivatives here. 6 times 2/3 is 4, so it's going to be 4x to the minus 1/3 minus 4. And then you solve this, our critical numbers. You set this equal to 0 and solve, and then you also say where this does not exist. And we don't need to go through the whole details. If you remember from last time, x equal 1 makes f prime of x equal 0, and x equals 0 makes f prime of x not exist. I guess I shouldn't put the d there. That's grammatically incorrect. X equals 0 makes f prime of x not exist. So these are our two critical numbers. We did this example a couple times ago. There's some details you got to work through to figure that out, but I remember. I'm here to tell you those are the two critical numbers. And so what do we do to do the second derivative test? We plug these critical numbers into the second derivative. Let's find the second derivative then. F double prime of x, we got to take the derivative right here. Okay, the minus 1/3 comes down here. I get minus 4/3 x to the, what's the new exponent? Negative 1/3 minus 1 makes it negative 4/3. And then this minus 4 just goes away because it's a constant, took the derivative. All right, that's the second derivative. Second derivative test says we plug the critical numbers into the second derivative. So I'm going to do f double prime of 1. I get minus 4/3 times 1 to the negative 4/3. 1 to any power is 1, so this is minus 4/3 times 1, which is negative. So x equal 1 is a relative maximum, right? Negative second derivative means this shape, and so your point is at the top of the hill. X equal 1 is a relative maximum. Okay, what about the other one? F double prime of 0. This is negative 4/3 times 0 to the negative 4/3. And this does not exist. Why does this not exist? It's 0 to a negative exponent. This means, of course, negative exponent always means 1 over, in this case, 0 to the 4/3. And this here does not exist. What's your interpretation of that then? That means that the second derivative test cannot be used in this case, and you must use the first derivative test. So in this example, the second derivative test got us one of them. The other one, unfortunately, you cannot use the second derivative test. So I'll just write here. So the second derivative test fails. Go back and use the first derivative test. It happens sometimes.